set and we are live and I'll start it again थोड़ा पीछे लेके.
So with PyTorch 1.0, the team has added a couple great features for converting your model into a serialized format that you can load into a C++ program. So there are two ways in general of converting your PyTorch model into a C++ script. The first way of converting a PyTorch model is known as tracing. So the idea behind this is that you can actually map out the structure of your model by passing an example tensor through it. So you're basically doing a forward pass through your model, and then kind of behind the scene, PyTorch is keeping track of all the operations that are being performed on your inputs. And in this way, it can actually build out a static graph that can then be exported and loaded into C++. So to do this, we use a new module in PyTorch called JIT. So JIT stands for Just-in-Time Compiler. So the way this works is that first you create your model. So in this case, we're just using a ResNet 18 model that we get from TorchVision. But really, this could be any model that you've defined and you've trained. And then we need an example of an input. So this can be just random values, a random tensor, but it should have the same shape of what you would normally provide to your model. So in this case, ResNet 18 is an image classifier convolutional network. And so we would typically pass in images with some batch size and 3 color channels. And these images are typically 224 by 224. So in this case, we're just passing in a single kind of fake image. And you notice this is just a random tensor. So this is not an actual image. It just needs to be an example input that is the same shape and size as your normal inputs. Then what we can do is pass in our model and the example to torch.jit.trace. And this will give us back a traced script module. And at this point, you can use your trace script module just like a normal module. So you can pass in data, and then it'll just do a forward pass through it, and it'll return the output, and you can look at that and use it like normal. Welcome to this lesson on using some really cool new features in PyTorch. So this is specifically features that are being introduced in PyTorch 1.0. What they allow you to do is export your trained models in PyTorch that you've trained in Python and export those to a version that you can then load up in C++. This is specifically useful for deploying your models in production. So production environments tend to require very low latencies and strict deployment requirements. For the most part, these environments are built with C++. So if you're going to deploy your model into production, for example, maybe like on some mobile device or a web app or an embedded system like a self-driving car, then typically your production environment is going to be in C++. And so you need to have your model in some format that is able to be loaded into that C++ environment. Now in PyTorch 1.0, we have these new capabilities where we can convert our model, which we've built and trained in Python, into sort of an intermediate representation that's enabled by this new thing called TorchScript. So TorchScript is an intermediate representation that can be compiled and serialized by the TorchScript compiler. So the idea here is that you first develop and build your network in Python, and you train it there, and find the best hyperparameters and such, like kind of that whole workflow. But when you're ready to deploy it, you will convert your PyTorch model into the TorchScript representation. And from there, you can compile it into a C++ representation. So there are 2 ways of converting your PyTorch model to TorchScript. So the first one is known as tracing. So the idea behind tracing is that you build your model and then you pass some example data through your model, like doing a forward pass through it. Then behind the scenes, what PyTorch is doing is it's keeping track of all the operations that are being performed on your input tensor. And in this way, it can actually build this graph of operations that are being performed on your inputs. And then once it has that graph, it can convert it to TorchScript. To do this, you'll be using a new module called JIT, so torch.jit. So JIT stands for Just-in-Time Compiler. So in this case, ResNet 18.
वापस वही चलाना, सॉरी मैंने.
So sometimes your model might use forms of control flow that don't actually work with this tracing method. So
वापस चला था ना कि वो वही एक चीज रिपीटेड वो किसी रीजन की वजह से बता रहा था.
So torch.jit input.
I don't know if it's the same
typically
one.
it accepts images of the side.
ये तो वही
We
किया
use
ना.
torch.jit.trace. So we pass in our model and we pass in the example, and it returns to us
वही था क्या? वो part तो repeated
Hey there.
था ही,
So
but I
I'm
don't
gonna
know if it was still 2.
that we get from
there.
TorchVision. But really, this could be any model that you've defined and you've
So if you
trained.
see,
This
ये एग्जांपल जिट
PyTorch
वाला वही है
is
जो
Keep++.
दूसरे वीडियो में भी दे रहा है.
So the way this works is that first you create your model.
So converting to TorchScript via tracing. हालांकि इसने बोला था कि उसमें दो तरीके हैं और तरीका बताते हुए सिर्फ
We're going to do
ट्रेसिंग
this
का ही बता
like
रहा
a tensor, and in this way, it can actually build this graph of operations that are being performed on your inputs. So we have an example given here. So we're going to just be using an example model. So ResNet 18. This is a convolutional network used for classifying images. We can get this model just from Torch Vision, and so we'll just use this as an example. So we have our model. So this can be anything you have built and trained yourself, or this is just an example here, but this same code applies to anything you would build yourself. We need an example input. So it doesn't really matter like the actual values in the tensor itself. It just has to have the same shape of what you would normally pass through your model's forward method. So in this case, ResNet 18 is an image classifier, right? So it expects images. So in general, you would have some number of images per batch. So here we're just going to use one image, 3 color channels, so red, green, and blue. And then it typically accepts images of the size 224 by 224. So we could just construct a random tensor that has the shape 1 by 3 by 224 by 224. Now with our model and our example, we use torch.jit.trace. So we pass in our model and we pass in the example, and it returns to us a script module. The script module is this torch script representation, but you can use it exactly like a regular PyTorch model. So if you pass in a tensor, like an image, it's going to give you the output that you would expect from a normal PyTorch module. So sometimes your model might use forms of control flow that don't actually work with this tracing method. So for example, you might have some if statements in your forward method that depend on your input. So things like this, they're fairly common in natural language processing problems. So then there is a second way to convert your models to TorchScript, and this is through annotation. So if you have a model like this, so typically you would subclass it from torch.nn.module, create your parameters or whatever else you need, and then have some forward pass. But here the forward pass has this if statement that depends on the input itself. So here the tracing method that we used before isn't going to work. So remember with that, what we did is we basically passed an example input through our network, and then in that way like traced out all the operations and built this graph. But with control flow like this, then the graph that you're going to build actually depends on the input that you put in. So instead, what we're going to do here is subclass from torch.jit.script module. And so remember when we used tracing that actually returned a script module for us. But here we are creating our own script module. And now with our forward method, with this control flow, we can use a decorator, so torch.jit.script method, and then it will appropriately convert this to a script module for us. So the cool thing about this is that you previously defined your module like this, and you got everything to work, you've trained it, and now you want to convert it for production, and all you really need to do is subclass it from script module instead of module here, and then add this decorator. So it's basically just 2 changes to the code that you already have, and you're ready to ship it to production after training. So now with either method of tracing or annotation to get your script module, you can serialize it to a file which can then later be loaded into C++. So to do this, you simply take your script module and use the save method, pass it in the file name or path where you want it to be saved, and then it will produce this file in your directory. And then with this file, you can load it into a C++ program and use your model just as you would in Python. Now let's see how we actually load our script module into C++. So for this, there is a requirement that we need libtorch. So this is the C++ API for PyTorch. And we'll also want to use CMake for building our actual application. So here we're just going to make a very simple C++ application that only loads in our module. And then if that's successful, it's just going to print out OK. So here we are including libtorch, and then we are creating our main application function. And this is going to take some arguments from the command line. So the way we're going to use this is that we're going to call our application from the command line and pass in the path to our script module, which we exported before. And here, this line is where we actually load in our script module. So we're going to create a shared pointer for our script module, and then we use torch jit load to actually load in our module itself. And so argv here is the path to our exported script module. And then if our module isn't null, so like if we actually did load in this thing, then we're going to print out OK to the standard output. So like I was mentioning before, we are using CMake to build our application. So this is an example of CMake list.txt that's going to configure how we build it. And specifically, it's going to be looking for the libtorch package. So find package torch. we get libtorch, you can just download it from the download page here on the PyTorch website. So if you download it and unzip it, then you'll get this folder with the structure. It looks like this. And so when we're building our application, we just need to point CMake to this library, and then it will automatically have all the headers and libraries and everything it needs, and it will compile our application for us. Then to build our application, we want to have our application directory look like this. So we have this top level directory of example app, and then include our CMake list.txt, which is up here. Just copy this, and then our actual C++ file. We'll create a build directory, then move into that directory. So then we will call CMake and we'll point it to our libtorch package, so wherever that is. And then the dot here will point it to our actual C++ files in the directory one above from here. Type make, and this should build our application. So if everything went well, now we just need to call our application and then pass in our saved script module. And then if it loads it and everything's good, then it'll return an OK for us. So that was just a really simple script. We weren't really doing anything with the model itself. We were just loading it in and making sure that worked. So we can add just a few lines to our existing application where we're actually going to pass some data through our model. So here we're just creating a vector called inputs, and then we're going to create a torch tensor of ones with the size 1, 3, 224 by 224, and going to insert this into our vector inputs. So we have our model loaded into module here, and we just call the forward method on this, pass in our inputs, and then we convert it to a tensor. And we're going to set this to this variable output. Now we can look at the values in output using output.slice. And so we're going to look at the first dimension. We're going to start at 0 and then end at the 5th element. Here's a nice little tip. If you want to learn more about the PyTorch C++ API, then check out the docs here. So pytorch.org, CPP docs. Okay, so now if we, again, build and compile this application, then run it, you'll see that we actually get an output from our model. This is a pretty simple example of how you use the C++ API and script modules. But using the same process, you should be able to start deploying your own models to C++ environments. So the general workflow for this will be building and defining your model in Python with PyTorch and training it there. And then once it's all trained, you can convert it to a script module, either with tracing or the annotations, and then serialize it with the save method. And then from there, you can use the C++ API to load it into a C++ application and go from there. Cheers.
ठीक है, आई थिंक इसमें तो कुछ खास करने लायक है नहीं. दिस इज रियली प्रोडक्शन वगैरह पे जाएंगे तो ठीक है.
Straight forward.
क्या बोलता है अपना डीप लर्निंग? आई थिंक मोरलेस हो गया. आई थिंक क्या बोलता है, कैसा रहा तुम्हारा डीप लर्निंग का सेशन पहला? इंट्रो टू डीप लर्निंग विद PyTorch. थोड़ा और हैंड्स ऑन और थोड़ा अपने को आउट ऑफ सिलेबस प्रैक्टिस करना चाहिए था. वो एक चीज़ है. लाइक डिफरेंट.
Good, very good. I think I haven't gotten into this level of detail. मैंने हर बार ऊपर से ही पढ़ा. तो it's good to see the actual implementations.
Internals, yeah.
And internals.
कल से अपन ये करते हैं, LLM चालू करते हैं, and hopefully we will get up to speed with the world, with the latest whatever is going on, agentic और ये और वो. Again, internals, not the peripheral.
हाँ. I mean, we still have an hour today.
Yeah, it's still an hour. So
क्या करना है?
वही अपना स्टैंडर्ड, क्योंकि आई थिंक वो जो 3 ब्लू एंड ब्राउन है वो अपने कंटिन्यूस रेफरेंस के लिए, हैंड्स ऑन के लिए वो नहीं, ऐसा ही कुछ एक ढूंढना पड़ेगा जिसमें हैंड्स ऑन चाहिए. और वो मैं तब तक ढूंढता हूँ. बट आज क्योंकि वैसे भी 1 घंटा है, मे बी वी कैन स्टार्ट विद दैट एज एन नाइस लिटिल इंट्रो. पहले तो मुझे ये देखने दो क्या मुझे ये करना पड़ेगा और क्या नहीं. पहले तो मेरा वाला हटा देता हूँ. ये पता नहीं मैं क्या क्या चीजें ये कर रहा हूँ. What is that we wanted to do? 3 blue and brown, right? 3 blue and brown. Neural transformers चाहिए था अपने को inside, and I think neural networks में next था वो, and large language model explain briefly about 1 घंटे में कर लेंगे अपन इसको. और let's make sure कि I've shared, ये sharing हटा देता हूँ और वो sharing कर लेता हूँ, which is what is a neural network. Okay, I think we are all set, and let's go 1.25. I think since you have also gone through this, I'll set it at 1.25. And with
Yeah.
yeah.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble.
Let's start from large language model.
Imagine you happen across a short movie script that describes a scene between a person and their AI assistant. The script has what the person asks the AI, but the AI's response has been torn off. Suppose you also have this powerful magical machine that can take any text and provide a sensible prediction of what word comes next. You could then finish the script by feeding in what you have to the machine, seeing what it would predict to start the AI's answer, and then repeating this over and over with a growing script completing the dialogue. When you interact with a chatbot, this is exactly what's happening. A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant. You add on whatever the user types in as the first part of that interaction, and then you have the model repeatedly predict the next word that such a hypothetical AI assistant would say in response, and that's what's presented to the user. In doing this, the output tends to look a lot more natural if you allow it to select less likely words along the way at random. So what this means is even though the model itself is deterministic, a given prompt typically gives a different answer each time it's run. Models learn how to make these predictions by
just to keep this a little bit of interactive, और आई नो कि वो एक लास्ट में उसके हाउ डज इट स्टोर फैक्ट्स टाइप के इसमें थोड़ा सा कवर करता है, जितना मुझे याद है. बट द पॉइंट इज देयर इज अ सिस्टम प्रॉम्प्ट, देयर इज अ यूजर प्रॉम्प्ट, राइट? विद दिस इज ऑल basically it's a prompt that you're giving the large language model. It's kind of a seed to start him off, right? And if it is just probabilistic filling up of next words that might come up and that it has learned in its corpus. So जैसे what follows is a conversation between a user and a helpful AI, AI assistant. User give me some ideas for what ये, या फिर ऐसे लिखते हैं कभी कि to AI you say कि let's say you are helpful medical assistant or something, and user is going to ask ये, and then तो the point is सिर्फ ये probabilistic होता तो हो सकता है वो क्वेश्चन को ही फिर कंटिन्यू करे, right? Because give me some ideas for what to do when visiting Santiago, and what other places are nearby वगैरह, ऐसा कंप्लीट करना चालू करे, लेकिन वो आंसर करना चालू करता है, राइट? सो अपार्ट फ्रॉम द फैक्ट दैट कि इसका कंटिन्यूएशन एक क्वेश्चन भी हो सकता था, राइट? कि इफ इट इज जस्ट डम्प टेक्स्ट जो मुझे प्रेडिक्शन के हिसाब से आगे बढ़ाना है इस लाइन को, तो एक कंटिन्यूएशन दूसरा उसका हो सकता है, या शांतियोगा से कुछ और भी हो सकता है, बट इट नोज कि इट्स आंसर करना है उसको. सो वो रोल प्लेइंग और वो एक जो भी पोस्ट ट्रेनिंग में उसकी ट्रेनिंग होती होगी, दैट इज ऑल्सो दैट एस्पेक्ट टू इट.
Yeah, that's a good point. I think the system prompt is kind of helping it determine that you have to give an answer.
तेरा आवाज थोड़ा
User
कट
query,
सा आ
or
रहा है.
is the system prompt determining that the LLM has to give an answer to this user query, or is something else doing that?
आई मीन टिपिकली तो सिस्टम प्रॉम्प्ट रहता है, जैसे इन चैट जीपीटी के पीछे भी एक सिस्टम प्रॉम्प्ट जो उसके कंपनी ने लिखा हुआ है, और ना भी रहता होगा तो, बट द पॉइंट इज कि एक सिस्टम प्रॉम्प्ट भी एक अल्टीमेटली एक जस्ट एडिशनल लाइन ऑफ टेक्स्ट है जिससे स्टार्ट होता है, फिर उसकी यूज़र की क्वेरी आती है. and then it plays into that role well, right? It assumes a personality and everything. The point is not just probabilistic completion of whatever it says before it, right? In that case, it can go all different directions, but then there is a little bit of knowledge as to sense of what he is, and उसका आंसर कहाँ से चालू होना चाहिए, ना कि बस प्रोबेबिलिस्टिक कंटिन्यूएशन करना है, जो सिर्फ इतना ही अब तक इतना ही वीडियो में किसी को दिखाऊं तो ऐसा लगेगा. तो इस पॉइंट ऑफ व्यू he handles it in his next videos. Anyway, let's continue.
Natural if you allow it to select less likely words along the way at random. So what this means is even though the model itself is deterministic, a given prompt typically gives a different answer each time it's run. Models learn how to make these predictions by processing an enormous amount of text, typically pulled from the internet. For a standard human to read the amount of text that was used to train GPT-3, for example, if they read nonstop 24/7, it would take over 2,600 years. Larger models since then train on much, much more. You can think of training a little bit like tuning the dials on a big machine. The way that a language model behaves is entirely determined by these many different continuous values, usually called parameters or weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind-boggling. To illustrate, imagine that you could perform 1 billion additions and multiplications every single second. How long do you think that it would take for you to do all of the operations involved in training the largest language models? Do you think it would take a year? Maybe something like 10,000 years? The answer is actually much more than that. It's well over 100 million years. This is only part of the story, though. This whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this, chatbots undergo another type of training, just as important, called reinforcement learning with human feedback. Workers flag unhelpful or problematic predictions, and their corrections further change the model's parameters, making them more likely to give predictions that users prefer. Looking back at the pre-training, though, this staggering amount of computation is only made possible by using special computer chips that are optimized for running many, many operations in parallel, known as GPUs. However, not all language models can be easily parallelized. Prior to 2017, most language models would process text one word at a time. But then, a team of researchers at Google introduced a new model known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers, and each of these list of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training. All of this data repeatedly flows through many different iterations of these two fundamental operations, and as it does so, the hope is that each list of numbers is enriched to encode whatever information might be needed to make an accurate prediction of what word follows in the passage. At the end, one final function is performed on the last vector in this sequence, which now has had a chance to be influenced by all the other context from the input text, as well as everything the model learned during training, to produce a prediction of the next word.
1 minute पीछे ले लियो.
Oh, dropped on a technical difficulty या by volition?
Yeah, no. Something went wrong. I think my internet went off.
हाँ, क्योंकि वो आवाज भी तेरा कट रहा था बीच बीच में जब तू ये कर रहा था.
हाँ.
जस्ट कहाँ तक सुना तूने?
ये
जो अपना
I think
डिस्कशन चल रहा था।
ट्रांसफॉर्मर जब उसने
अच्छा,
बोलना शुरू किया कि गूगल started a new architecture for Trump.
ओके। वो भी कहाँ से किया एक्चुअली? ये क्या? ये देखा था क्या?
is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, one word at a time, but then a team of researchers at Google introduced a new model known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers, and each of these list of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transform.
ये जो पार्ट है
And refine the meanings that they encode of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around.
this side by side words influencing each other और उस हिसाब से वो एक दूसरे का ऑर्डर और वो कॉन्टेक्स्ट जान लेते हैं इन अ सिमिलर सेंस। वैसे देखा जाए तो ये भी था राइट अपना CNN में जब अपन कर्नल वगैरह लगाते थे एवरेज आउट करते थे बाकी का मतलब सेंटर वाला पिक्सल बेस्ड ऑन इसका सो इट इज़ देयर बेसिकली नेबर्स। आई मीन इट वाज लोकलाइज्ड लाइक हर एक इमेज का हर एक पार्ट एक दूसरे को इन्फ्लुएंस नहीं करता था बट जितना भी ग्रिड था उसका 3x3 वाले तो एक दूसरे को इन्फॉर्म करते थे राइट अपने कर्नल के हिसाब से।
Correct. Yeah.
All done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training. All of this data repeatedly flows through many different iterations of these two fundamental operations. And as it does so, the hope is that each list of numbers is enriched to encode whatever information might be needed to make an accurate prediction of what word follows in the passage. At the end, one final function is performed on the last vector in this sequence, which now has had a chance to be influenced by all the other context from the input text, as well as everything the model learned during training, to produce a prediction of the next word. Again, the model's prediction looks like a probability for every possible next word. Although researchers design the framework for how each of these steps work, it's important to understand that the specific behavior is an emergent phenomenon based on how those hundreds of billions of parameters are tuned during training. This makes it incredibly challenging to determine why the model makes the exact predictions that it does. What you can see is that when you use large language model predictions to autocomplete a prompt, the words that it generates are uncannily fluent, fascinating, and even useful. If you're a new viewer and you're curious about more details on how transformers and attention work, boy do I have some material for you. One option is to jump into a series I made about deep learning, where we visualize and motivate the details of attention and all the other steps in a transformer. But also, on my second channel, I just posted a talk that I gave a couple months ago about this topic for the company TNG in Munich. Sometimes I actually prefer the content that I make as a casual talk rather than a produced video, but I leave it up to you which one of these feels like the better follow-on. The initials GPT stand for Generative Pre-trained Transformer. So that first word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the prefix insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript.
This sentence comes from a model going the other way around, producing synthetic speech just from text.
All those tools that took the world by storm in 2022, like DALL-E and Midjourney, that take in a text description and produce an image, are based on transformers. And even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt, and then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning. And it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple decades have proven to scale remarkably well. What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be formatted as an array of real numbers. This could simply mean a list of numbers, it could be a two-dimensional array, or very often you deal with higher dimensional arrays, where the general term used is tensor. You often think of that input data as being progressively transformed into many distinct layers, where again, each layer is always structured as some kind of array of real numbers, until you get to a final layer which you consider the output. For example, the final layer in our text processing model is a list of numbers representing the probability distribution for all possible next tokens. In deep learning, these model parameters are almost always referred to as weights, and this is because a key feature of these models is that the only way these parameters interact with the data being processed is through weighted sums. You also sprinkle some nonlinear functions throughout, but they won't depend on parameters. Typically, though, instead of seeing the weighted sums all naked and written out explicitly like this, you'll instead find them packaged together as various components in a matrix vector product. It amounts to saying the same thing. If you think back to how matrix vector multiplication works, each component in the output looks like a weighted sum. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters that transform vectors that are drawn from the data being processed. For example, those 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices. Those matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories to understand what that type does. As we go through, I think it's kind of fun to reference the specific numbers from GPT-3 to count up exactly where those 175 billion come from. Even if nowadays there are bigger and better models, this one has a certain charm as the first large language model to really capture the world's attention outside of ML communities. Also, practically speaking, companies tend to keep much tighter lips around the specific numbers for more modern networks. I just want to set the scene going in, that as you peek under the hood to see what happens inside a tool like ChatGPT, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of a risk getting lost in the sea of billions of numbers, but you should draw a very sharp distinction in your mind between the weights of the model, which I'll always color in blue or red, and the data being processed, which I'll always color in gray. The weights are the actual brains. They are the things learned during training, and they determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them, and the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words. These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, for the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example, for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way the queen is used in training data is not merely a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions, it's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257, and again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12.
ये एम्बेडिंग लेयर का जो था ना, वो हर एक वर्ड का एक स्टैटिक रिप्रेजेंटेशन है, राइट, इन टर्म्स ऑफ वेक्टर.
Word, not word, like token.
ठीक है, लाइक जस्ट लाइक ये सिंप्लीफाइड वे में अगर मैं
Yeah.
तो वो एक स्टैटिक रिप्रेजेंटेशन है, राइट. मतलब मैं एक एम्बेडिंग मॉडल लूँ और उसको एक वर्ड दूँ, किंग वर्ड दूँ, तो वो मुझे उसका वेक्टर देगा. और क्योंकि वो ट्रांसफॉर्मर मॉडल के थ्रू, आर्किटेक्चर के थ्रू जा रहा है, उस वर्ड का कुछ और मीनिंग हो सकता है, तो वो सोकिन होके वो अपडेट होगा. दैट्स बिकॉज ऑफ द ट्रांसफॉर्मर आर्किटेक्चर. बाय एम्बेडिंग मॉडल इटसेल्फ, सिर्फ उतने को ही देखूँ तो
It will be like word to vec.
word to vec, right? But my question is, if it was as simple as just word to vec, why does in a higher dimensional space, जो वो बोल रहा था कि it has learned to associate king and queen belong together, या फिर king and queen के बीच का difference should be man and woman का बीच का difference. How is that relationship captured when you are just encoding a text to a number? Right? That is,
I think that is only because of the embedding model itself being trained on a large corpus and having some 12,000 dimensions or whatever.
right.
It's because of that. It's not a simple one-to-one mapping saying A is
Which is
so and so
kind
vector.
of like saying कि ट्रांसफॉर्मर की तरह वो भी, हालांकि वो उतना पावरफुल नहीं होगा, दैट्स अ सेपरेट थिंग, बट इन अ सेंस इट इज जस्ट नॉट न्यूमेरिकल रिप्रेजेंटेशन ऑफ सम टेक्स्ट, right? Or just that it is efficient, but it understand meaning, just like transformer is supposed to understand the patterns and underlying patterns inside ये. तो embedding भी तो वही कर रहा है in a sense, right? क्योंकि अगर उसने दो रिलेटेड चीज़ों को एक साथ क्लस्टर करना सीखा है, तो उनको कनेक्ट भी कर सकता है कल, एक छोटे लेवल पे देखा जाए तो. एक ही चीज़ और मैं देख रहा था कि मैंने वो जब दिखा रहा था तो मैं इसको एक गणित जो उसने किया था उसमें मैं थोड़ा कहीं और देख रहा था, ये बाद में फिर काम आएगा, इसलिए मैं वापस एक बार इतना ही देख लेता हूँ मैं कि
is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257. And again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. How much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversation individual words could represent. The network can only process a fixed number of vectors at a time. Who had achieved his post after, for example, might progressively get tugged and pulled by various blocks in this network. Was a king who lived in Scotland and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently.
To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding, we see least favorite teacher, and also if you give me some leeway by letting me pretend the tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over 1 billion. A small, but not wholly insignificant fraction.
Can you talk a little bit about unembedding? Like embedding was your...
Yeah, I think it's just once you finally get जो हमने इसमें भी देखा था RNN LSTM में, तुमको फाइनली जो वेक्टर आता है उसका तुम एक सिग्मॉइड फंक्शन डाल के उसका एक वर्ड निकालते हो. So you are doing the same thing here in a way where you're getting a final probability distribution and saying, okay, this then belongs to this word most likely, and that's why you output Snape in this case, which we said. So it's kind of unpacking what you did in the first, which was packing. तो जो तुमने embedding किया है उसको unembed करना है. So you just jump to the last and saying, okay, how will this eventually work in the end? It is the same way as it has worked in the beginning, just the reverse. तो ये softmax use करके उसका एक probability ये निकालना है.
Right. तो ये जो पार्ट है, what these two matrices are, right? तो ये वाला जो पार्ट है वो तो है कि उसके कॉन्टेक्स्ट विंडो में से जो लास्ट बचा हुआ है, मतलब कॉन्टेक्स्ट विंडो में पूरा है, उसके बाद उसको प्रेडिक्ट करना है, राइट? वो वाला इनफैक्ट नहीं, उसके कॉन्टेक्स्ट विंडो का जो लास्ट वर्ड है या टोकन है जो भी है, राइट, वो ये है. और हैविंग गॉन थ्रू ऑल ऑफ द अटेंशन लेयर सो फार, hopefully we believe that it has soaked enough information कि इसमें है. But then this has to be multiplied with the matrix weights of the that unembedding layer also, right? तो मीनिंग तो वगैरह इस सीक्वेंस में आ चुका है बिकॉज ऑफ द अटेंशन, बट ये वो है जो क्या डिनोट कर रहा है, या ये भी
वेट्स है ऑफ द
these are not attention layer का weights though.
The weights of the transformer.
Weights of the transformer, but if you look at layer by layer, these are not attention layer के weights. These are at the very end, सब forward वगैरह करके ये वाले weights है, right? तो एक conceptually मैं अगर ये समझना चाह रहा हूँ कि ये weights क्या करा रहे हैं इससे, इस पूरा मीनिंग तो इसमें आ चुका है, राइट? जैसे वो स्टार्टिंग में एम्बेडिंग वेक्टर के साथ जो पूरा स्टैटिक मतलब था उसका ऑन दैट हायर डिमेंशन वो था. अटेंशन के थ्रू जाने के बाद उसमें रिच मीनिंग आ गया है, ऐसा मीनिंग आ गया है कि मैं अभी नेक्स्ट वर्ड पता कर सकता हूँ, और वो निकलवाने के लिए ये मैट्रिक्स है, राइट? अभी तक के जो मैट्रिसेस थे जो अटेंशन लेयर पे आ रहे थे वो इनमें मीनिंग डालने के लिए थे, और अनएम्बेडिंग उसमें से वो मीनिंग निकालने के लिए है क्या, लाइक जब फाइनल प्रोबेबिलिटी निकलवाने के लिए. एंड यहाँ पे अगर तू देखेगा तो वो जो कैलकुलेशन करता है तब वो सारे लेयर्स
process.
दिखेंगे उसके.
Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension.
So each
तो उसका shape is same as embedding,
हाँ,
right?
इसका शेप इज सेम एज द वोकेबुलरी इनटू 11,000 क्या था, और दिस इज जस्ट सम रैंडम नंबर, दिस इज कम फॉर द फर्स्ट टाइम. ये चैट
think वो
जीपीटी का,
dimensions है ना?
हाँ,
Is it not the dimensions?
वो 12,000 कुछ था ना.
हाँ, तो he just said no. The shape of it is just थोड़ा सा 10 seconds back करेगा तो
Dimension. Matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over a billion. A small, but not
ये कह रहा था मैं, ये जो सारे लेयर्स है ना, ये अनएम्बेडिंग, होपफुली आई डोंट नो कि ये सीक्वेंशियली है कि नहीं.
same है, exactly same है ना?
हाँ, that's fine. I'm not talking about the shape as such. What I'm trying to get is conceptually, like intuitively, what that unembedding is trying to do. Are you saying that it is just trying to do the exact opposite of this?
Yes. What is embedding doing? It is giving you a vector of 12,000 dimensions for a particular word. And unembedding is taking a vector of 12,000 times 50,000, which is 1.2 million or billion, whatever parameters,
Okay.
and giving you a word out of it.
ठीक है, exact opposite कर रहा है, ठीक है.
Exactly.
I was thinking कि वो क्या जो दूसरा मैट्रिक्स था वो अलग था क्या उससे. No, ठीक है.
wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini lesson for the chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1 and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max, in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature in certain thermodynamics equations, and the effect is that when T is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform, and if T is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting T equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, once upon a time there was A, but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits. Or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. A final version should be up in public in a week or 2. It usually depends on how much I end up changing based on that review. In the meantime, if you want to dive into attention, and if you want to...
कॉर्नरस्टोन पीस कल करते हैं.
हाँ, I think काफी पैक हुआ है आज in terms of